Okay, so next up we have Vadim, and he will be talking about a very long topic. Google Security Chip H1, a member of the Titan family. Big welcome.
Thank you. So H1 is a chip which was designed by Google. At some point, there are actually a lot of paranoid people at Google, which, and rightly so, I might say, who thought that they need to be able to control everything from the very beginning. And so there is a group of chip designers, which I'm not part of, certainly, which designed this chip with many different applications in mind at Google. And at some point, it was decided that Chrome OS would be also a good use case for that. And Chrome OS actually gave them a lot of inputs into what could be done special for the typical secure computer user computers which are used by people outside enterprise. And this chip came along, and so this is what's inside. So it has an ARM core, and then it has fairly limited resources. It has 8 kilobytes of ROM, which is programmed at the chip factory, so it cannot be changed. It has 64 kilobytes of SRAM, 500 kilobytes for flash. One important piece, it has a crypto engine, which is basically speeds up crypto operations, and it also provides secure key ladders, which can be enabled or disabled. The keys could be hidden depending on the mode of operation of the chip. Then it has a bunch of peripherals, USB controller, I2C for master and slave, SPI master and slave, GPIOs, UARTs. It has also a very good random generator. I'm not pushing this. So the random number generator is a lot of hardware effort was put into designing this, and it is claimed to be truly random, as random as it could be. And it also has this, and it has the circuit for sensing a debug cable plugged in, and then it kind of brings to life a whole new personality of this chip, which we can talk later about, or will talk later about. And of course, there is a PinMax, which allows to connect different peripherals to different pins on the chip. And there is this so-called RBox, which is a subsystem which controls power and reset and is completely independent from the CPU. It's run on a very low level, and it's one of the things which contributes into the root of trust of Chromebooks. So this is about the flash memory, how program fits into the flash. So we have 512 kilobytes, but to be able to recover from bad images and to avoid breaking the system, this flash is actually split in two halves, which are very symmetrical, almost symmetrical. So there is 16 kilobytes of so-called read-only. It is, I guess it's a misnomer because it still can be changed. And then there is 230-something kilobytes, which is dedicated to read-write. And then there is 12 kilobytes, which is dedicated to non-volatile memory. And this is duplicated, so there are two of these halves. And so each read-only and read-write both, they have the same header preceding them. And the header has all kind of information in it, including means of integrity check and verifying the version of this header. So basically, when the code executes, each early version, we have ROM, read-only, and read-write, can check the later the later stages version, and decide which one to run. Each earlier stage can decide which later stage to run based on the header contents. So the code, all code for this CR50, this, by the way, this particular project running on the chip is called CR50 for not entirely clear. I think this is one of the isotopes of chromium, which is like less and less stable, but this actually, it's not the rightful name anymore. So the code comes from, it is from the ChromeOS EC repo, and the board files are in board CR50, and chip files are in chip G, and this is the Git server which stores this code. So someone mentioned today earlier that TPM from Infineon is completely closed. We don't know anything about its internals. I can say that I'm running a little bit ahead of myself, but the code, the TPM code on this device is completely open. It is courtesy of Microsoft, actually. We have some early versions retrieved from some Microsoft documents which were put on their open source license and integrated into this chip, so it is totally transparent. So I want to say a little bit about firmware updates. We kind of were thinking about this, and it kind of evolved while we were working on it, but what we ended up with was that the chip, by the way, I wanted to mention this here, but I didn't. So it, along with this 512 kilobytes of flash, it also has this so-called info space, which is also essentially flash, but it is not accessed directly. It can be, it needs to be enabled in a special way. It is split into four, it is just 2 kilobytes of it. It's split into 4 pages. So, and one of those pages is used for storing chip properties. So each chip gets assigned a board ID, which is just a 32-bit word value, which happens to match the name of the board in ChromeOS speak. And then this value is also saved inverted, so that no erasing one bit can go undetected. And it has the board flags, which yet another knob we can use to control what images run on this system. And it also has a 512 byte space, which actually used as 128 bits. What happens is that this bitmap space, this info1 space rather, it is very sensitive to write operations, and you pretty much cannot write more than 4 times into the same 32-bit word. So this is why we had to pretty much use a byte for word for a bit in that case. So, and then the image which which runs into on this device. So this is now the header I'm talking about. So this header also has the bitmap, the board ID, which consists of board ID mask, and board flags, and the version, which is just 3 arbitrary numbers, and the timestamp. So what happens when the image is loaded on the chip? The earlier stage checks that the bitmaps match, so that if a bit is cleared in this space but not in this space, the image is not accepted. Then it also checks that the board ID match, and of course we can create an image. The mask defines which bits from board ID are used for comparison. So if we set the mask to 0, this would mean that this image can run on any device, on any chip. But we can also, if we want to release an image which can run only on certain chips, on certain boards, then we can set this board ID mask to all ones, and the exact board ID will have to match. And then there is the board flags field, which also, again, any flag set to 1 on the board in the chip space must be set to 1 in the image, otherwise the image will not be accepted. So all these kind of tricks are necessary so that we can this allows this to be very flexible. We can both create an image which would run on any chip, or we can create an image which would run only on certain chips, only on certain boards, which have only certain flags set. This allows us to release a test and experimental firmware, and we are not afraid that this would leak into the open and start running on all devices. So that's how the updates are controlled. So major functions of this chip are, which this chip provides in the system, are guaranteed reset, including battery cutoff, then closed case debugging, which is this extension which was put into the chip based on our requests. The verified boot is pretty much a TPM, and then another nice thing is that being able to control the firmware of this chip allows us to tightly integrate it with the rest of the Chrome OS and make it support a lot of Chrome OS features which make Chrome OS more usable and more user and manufacturer friendly. So reset and power are controlled by this unit which we called RBox in the beginning here. So as I said, it is pretty much separate block on the chip, and it has a few functions. So first of all, it allows to provide unspoofed reset. This is a keyboard matrix which actually goes into the EC. So one of the components of a laptop, of course, is the embedded controller, which, among other things, controls power to the AP, and it controls the keyboard, and it controls the reset of the system. So we want to be sure that if the user has a way to reset the EC in an unspoofable way. So for that, the keyboard matrix, two elements, one row and one column, go through the RBox, and then when the user pushes the power button and the refresh button, these signals in RBox hardware and RBox logic make sure that it generates the EC reset signal, so that this basically gives the user a guaranteed way of resetting the system which cannot be spoofed. Another nice capability is the ability to control write protect to the flash where the BIOS is. So earlier Chromebook versions required the user to open it up and remove the write protect screw to allow updating firmware. With this chip, in a controlled environment, the owner of the device can enable write protect without opening up the chip. We'll talk about this a bit later. And another nice feature of this is the battery cutoff, so that if the user presses these two buttons and removes the AC cord, this generates a pulse on the battery's cutoff input, and the battery basically disconnects itself from the system. So this makes it easy for shelf storage of the device for a long time, and then just plugging in AC power revives the battery. So TPM interface it's basically a function which used to be implemented by Infineon chips in Chromebooks, but in this case it is a TPM2 specification. The H1 can be connected to the AP both over I2C or SPI. This is controlled by bootstrap resistors, which are read when H1 is reset. And the important distinction is that the TPM reset is not H1 reset, so that the H1 stays up at all times and it controls the system. TPM reset is just the resetting of the task, which one of the parts of software. It's kind of, it took a little, or maybe quite a few tricks to make it work right, but this is why I mention it here. So TPM support of verified boot in Chrome OS is not new, but it also ported into TPM version 2 specification. So TPM contains the NVMe indexes for rollback counters for firmware and kernel. So this is AP firmware, obviously, so that the older versions of firmware cannot be run on the system when there is a need to roll forward. Another AP is application processor. It's the main CPU of this. So I guess that's kind of a terminology. So each laptop or PC has the application processor, which is the x86 in most cases, or ARM. And then they has the C, which is a smaller device which controls the power for the rest of the system. And now it has this H1, which controls the C, basically. So it also stores the cache of the memory reference code. There was some talks about how, I mean, Julius mentioned this for ARM, but it is even more painful for x86. Memory initialization on a cold CPU on recent x86 devices takes 30-40 seconds for the DDR controller, or memory reference code, I should say, which comes from Intel and is a closed code, unfortunately, to train memory and figure out how it should be run. So it's like 40 seconds for boot is quite long. So what we do is once this memory reference code ran and calculated all the parameters for this particular controller, for this particular run, it saves all this memory, all this information into the flash and calculates the hash of it, and we save the hash in the TPM in one of the indices. So when the system reboots, it reads the memory reference code cache from flash, compares the SHA, and if it is okay, then it goes right ahead. And this allows us to compress the boot time immensely. Another thing is the firmware management parameters. This is a thing which allows enterprise managers to prevent, for instance, turning Chromebook into a developer device. So that if enterprise buys a bunch of Chromebooks, they don't want the users to be able to replace their firmware, even though otherwise we want Chromebooks to be completely open. So this firmware management parameters is a set of flags which are saved in the TPM, stored in the TPM, and if certain flags are set, the device will not turn into dev mode, even though the user will try to turn it on, convert it. And the device mode state is also saved there, so that even if a user puts their completely different firmware, the device still can run in developer mode. So this is how the closed case debugging system works. So it is possible to enable it only when user physical presence is confirmed by pressing the power button a certain amount of times in certain modes. But basically what happens, there is a debug cable which is plugged into the USB-C interface, and the debug cable creates very specific voltages on the two of the CC lines, which the chip can detect. And then once the chip detects this, it can enable USB controller to channel all UARTs into the I2C SPI interfaces into the USB endpoints. So there are also SBU lines are used for creating for keeping the USB interface with the rest of the host, basically. So once this debug mode is enabled, which again can be enabled only if the device is not in developer mode, so that the user first has to have their Chromebooks converted from normal, so-called normal mode when the boot process is fully controlled, to the developer mode where things can be changed. Then the user has the ability to enable this functionality through giving the device certain commands from the Linux prompt, Then once this so-called SUSI cable plugged in, which creates this voltages on the CC lines, all this magic happens. So at this point, the user can disable write protect so that both EC and AP flash chips can be written, and then the muxes which connect SPI buses from EC and AP to their respective chips can be switched, and the SPI master interface on the H1 can control these flash devices. So basically, this is the way for the user to replace firmware on the computer, and this is what makes it open. And sorry, we have I2C interface, which in certain cases it is used for programming flash on some ECs. It also used for power management when the device is still in development. This power management hardware is not populated on production devices, but it is very helpful when the device has been debugged still, so power people can always know what's going on there. So and again, this is what makes this chip very useful and helpful for Chrome OS, because in newer designs there is not even some of them are glue shut, so that one can't open them to remove the write protection screw, but we still want them to be accessible to users so that they can do what they want with their devices. So, and these are a few things which this chip allows the rest of the system, like a Chrome OS as a whole, to achieve. So a lot of them related to servicing the devices when they are returned from users. So for instance, RMA verification is a mode when a Chrome OS device which was returned from by the user in the store, they don't really want to send it back to the factory or to the RMA center if they don't have to. So one of the means of verifying that, they want to be sure that the AP and AC firmware hasn't been altered in this computer by the user before they returned it. So this magic SUSI cable I was talking about connects the device on the test and the master Chrome OS device. And the master Chrome OS device sends a command to this H1, which makes sure that the H1 puts the rest of the system into reset. And then the master tells the H1, read the following sections of flash and calculate their hashes. So, which the H1 does, and the master has a table which contains the values from these hashes, these areas, hashes these areas are supposed to have, and compares them. So if they match, this means that the firmware hasn't been modified, so that this Chromebook can be just reimaged and put back on the shelf. If they don't match, this means something else needs to be done, so it has to be sent to the RMA center. And this is what happens in the RMA center. So we still have this. So one of the things the RMA center will want to do is to reimage the flash of the device, of the computer. And for that, they need to enable write into the flash. So again, instead of opening the device, removing the write protect screw where it is, as they do today with the devices, or they had been doing until recently, and this is something they can't even do with the glued devices. We have a mechanism to allow authenticated users. So basically, this is the exchange between the Chromebook and the RMA server, where the RMA server can authenticate the user. It also can authenticate that this is the device which claims it is, and then send the user a code which allows to disable write protect. So this is done using ACC Diffie-Hellman algorithm. On the H1 side, it generates a random number which it uses as a private key for a certain ECC curve. Then it calculates the public key, and the server public key is a well-known number, of course. So then the H1 calculates a secret, knowing its private key and the server public key in this ECC space. And then it creates a challenge. Then it calculates the authentication code, which will allow to unlock this board. So to calculate this code, it takes the secret, this private key, it calculated the board ID, device ID, and then creates an HMAC of them, which ends up being a 40-bit value. And then it creates a challenge for the server, where it uses the server, which it uses its own public key, which was derived from the private key, in the same board ID and device ID, and send them to the server. So the server verifies that the authenticated user has rights to modify firmware for this particular board ID. Board ID is exactly, board ID allows to match a device, a Chrome OS device, into a certain model. So that if this is a Samsung RMA center, they don't want to allow them to modify Acer devices. So this is why board ID is part of this. So basically the server verifies all this information, and then it recalculates the same authentication code, because it can figure out the secret based on this product, again in this particular SCC space, and then it returns the authentication code to the operator, I should say. Yeah, this QR code here is the indication that once the H1 calculates this challenge for the server, the Chrome OS device displays this QR code so that the operator can take a picture. This will direct them to the server, to the certain server URL, which will include this challenge. And the server will verify everything and display that 40-bit value, which is like 5 characters. And the user will have to type that 40-bit value on the Chrome OS console. And once this value matches, the H1 checks the match. And if there is a match, it wipes out TPM, disables write protect, and reboots the device. So at this point, all the previous user information is wiped out, and the device is ready to be reimaged by the RMA personnel. So another nice extension is the pin login feature, which basically, this is a typical use case in schools, for instance, when there are several thousand of students and several thousand of Chromebooks in the school, and they don't want to tie any Chromebook to any student, and they don't want the students to have to type in long passwords, because it's sometimes tedious and kind of considered a bad user feature. So there is a map of, so basically the pin is like 4-digit very low entropy value, which the user can enter instead of their password. But we don't want the users to be able to try many things, obviously, and we don't want the user to be able to do this too quickly. So all this code running on Chrome OS side, it creates, for every user, it creates this structure which includes information about the user, and then it keeps track of how many attempts were made, when was the last attempt made, matches the PIN code to the actual user password, which allows to mount user's file system when user logs in. And it is protected by the MAC calculated by the H1. So each time a user wants to log in. And so these are the nodes which hold information about the users, and the rest are just hashes of the underlying nodes. This is a Merkle tree. Each one stores the root of this tree, and the fact that each one stores it guarantees that there is no way, for instance, for the user to power cycle the device and then turn it back on, and the history will still be there. And basically, this provides additional level of security for this feature. And yet another thing is the U2F support. This is pretty much, it implements the standard FIDO protocol, but the key is stored in the H1, and the power button again is used as the physical presence button, so that there is no need to plug in a separate U2F key into a Chromebook. The user can just use it for second factor authentication as it's supported by H1. So that's about it. If you have any questions. All right, if there are some questions.
Questions? Let's start here.
Quick question. You talked about disabling write protect. Could you explain about how it enables back?
How it enables
What's
back?
the conditions to re-enable write protect after you're done?
Well, first of all, there is the when you're so when this CCD is enabled, one of the UARTs which are available through this through USB is the UART of this of the H1 itself. Basically, you have access to its console, so you can write enable, write disable on the console. Then it has this. So the CCD mode has a list of properties, and one of them is flash write enable, what state it is in. So if the user, even if the device is in developer mode, the user can set this property that if CCD is closed, CCD is a closed case debugging. If the session is closed, then the write protect is enabled, even though the device is in developer mode. And the CCD, once user enables CCD, it can protect it with their own password, so that you enabled CCD, you made some modifications, you disabled write protect, close CCD, then you can give this device to anybody else without knowing the password. They cannot reopen the CCD, even though it is in dev mode. So basically, it prevents modifications unless the user really wanted them to happen.
Okay, two questions from me. I'm not sure about the marketing of H1 chip, but does Google will sell that for integration in other hardware?
That's a kind of interesting question. What happens is that Google could, be selling these chips, but the thing is that the users won't be able to create their own firmware for those chips, because the chips are, as we talked about here, all these headers, all these signatures, basically the very first key is saved in ROM, and then the RO image, it has to be signed with this key the ROM knows about, and this is a very tightly guarded secret, of course. The RW is something which kind of is more lax, but it's still a key which the RO now contains the public part, so that it has to be signed. So there is no way for someone to create a firmware and run on this chip because of this.
Okay, so probably this is related to my second question. What about the ability to inspect firmware and ROM content by third party?
So this ROM is closed, and it mostly deals with initializing the crypto engine and the random number generator. I don't really know why would it be, or I should say, without knowing details of this hardware, which is not open, you probably won't deduce a lot from this 8 kilobytes ROM. So this is why, and as I said, this was designed in a different group, which and this chip is used in many other applications. So this is probably not something which will be shared anytime soon. But the rest of the firmware, actually the RO is also not released. It is, but all it does, it also initializes some more hardware and verifies the RW. It's two of its roles in life. The RW is coming from this repository.
Hi. One question about the TPM and the verified boot. Actually, the TPM itself does only measured boot, right? So if you do verified or secure boot, how do you interrupt? Because actually, this is like actively prohibiting the application processor to start?
Yeah, that's, again, this is not new. This is not something new which was introduced into Chrome OS with this chip. The Chrome OS uses TPM for verified boot from the very beginning. And what happens is that the role of TPM in this case is just storing the version numbers of the firmware. So the root of trust for the AP is also in read-only. So the idea is that flash, where the code runs, the read-only cannot be changed. I mean, there are ways to change it, but for this level of security we want to provide and we promise, it relies on the fact that the user didn't modify the read-only firmware for the AP. And once read-only firmware starts, it verifies the integrity of the read-write part on the AP. So the integrity can be verified like this, and then it could be a case that there is a compromised read-write firmware which we want to replace. So for the key the firmware is signed with has a version in it, and the version is stored in the TPM. So when the newer firmware runs, the read-only firmware detects that the running version number is higher than the version stored in the TPM, and it updates the version stored in the TPM. And before it starts the read-write firmware, it locks that particular index in the NVMe. So this is all it does basically. So this is how. And if the firmware, for instance, the key number, the version in the firmware is lower than the version in the TPM, it shows this screen showing your system is damaged. Chrome OS system is damaged. You need to repair this basically, and it falls into the so-called recovery mode.
Maybe follow up because for me it's still not clear. So are you actually using the H1 to verify the application processor firmware?
No.
No.
The question is, where does that code run, which does the comparison and the decision?
That code runs in the AP firmware. All the H1 does is stores the number, and that number cannot be modified unless the read-only firmware is running, and we trust read-only firmware.
Thank you. My name is Dimi, and I have two questions about the design. So the one is the info memory, and the other is about the reset. And I can actually answer maybe the question that was before a bit, that in general the TPM does not have a storage to store the measurements and do the processing. TPM in general only measures and has internal PCRs, and that's my question related to. So the actual integrity measuring software or managing software is actually run by the application processor. So the question about the info, if you can go back to your diagram. So the info memory is a special memory that is restricted access. The question is this protected only by the MPU, or this is actually in hardware isolated memory that you have some hardware procedure to gain access?
Yes, you have, well, the hardware procedure controlled by software.
So is it a memory protection unit, or is it a more specific hardware procedure?
You can call it memory protection, yes.
Okay. And then the TPM reset is not a H1 reset.
Right.
That's a trade-off.
No, it's not a trade-off. That's basically, that's the,
That basically to what it means to me, because we're using TPMs in ours, like I'm working with TPMs. So what does this means to me is the H1 can be running and can be holding my TPM in reset. This is how it sounds to me. It means that the TPM reset is separate and can be held by the H1,
yes, this is
basically
true.
bricking my system.
Well, H1 can do a lot of damage to your system, even without,
Yeah,
even without holding TPM.
Yeah, but it could be basically no denial of service without just doing anything else by just holding a reset.
Yeah, you don't, as you're saying, like if you look at this,
Yeah, I
there
know
is-
you have all the SPI access, but you need to enable the debug. I'm talking about remote where I gain access to the H1 firmware or whatever, and then I can just apply reset. Do the TPM, my system won't even boot.
you can apply reset to the EC and like you don't worry about TPM. It's like everything is completely
So why
shut
this
down.
trade-off? Why is this trade-off?
This is not, again, this is not a trade-off. This is actually intentional because we want the closed case debugging running even when the AP is in reset.
Okay.
So, but we don't want the TPM to be to miss the reset because when the AP is reset, the TPM has to be reset to get into the highest security level. So this is why the H1 firmware is running. It can give you all the access to these things, to program these, to the consoles, to your measurements, whatever. But it also guarantees that when the EC is reset, when the EC reset pulse is generated, the TPM is reset also. This guarantees that the TPM
So it
is in
happens at the
sync.
same time.
It happens at the same time.
That's guaranteed.
This is guaranteed that the TPM is in sync with the rest of the system as far as the EC and AP are concerned.
Okay, quick last question. Do you have a time estimate for when the open silicon design will be released? And then doesn't have to be Google selling? Because no, but that was announced. It was announced that the Google will be opening the design of the chip eventually, making it possible for manufacturers to produce, and then you as a third party can buy from someone who got the design from Google, develop it further, and fabbed their own IC.
The SV300 is an ARM design.
Yeah, but I'm talking about the H1. They said that they're going to open the H1.
I don't know anything about it.
Okay, thanks a lot.
Sure.
Thanks a lot for answering.
So what's Chromebook's threat model around limited physical attackers regarding closed chassis debugging? So are there authentication or unlock mechanisms for holding the system in reset and having write access to SRAM or read-only memory?
Well, that's a good question. We always balance between providing high level of protection on one hand and then still keeping these things open to the user owns this, and the user should be able to do anything with it if they so desire. So for CCD to allow access to the device, so a few things have to happen. First of all, this firmware management parameter has to allow enabling the device mode on this Chromebook. So if this Chromebook is enterprise enrolled, then there is no way to switch into the so-called developer mode. So if this is not the case, so this is a hobbyist or any user who has this, so they have to switch Chromebook into the developer mode, so-called developer mode. This is the inherently less secure mode where the user is supposed to be allowed to replace the firmware. The write protection is still enabled. So in this case, when the device is in developer mode, the user can send the command through the interface from the AP to the H1 and tell it, I want to open CCD. And at this point, the H1 will request the user to indicate physical presence. So the user will have to keep pushing this button for a few minutes in different cadence. This basically confirms that the user is here at the device. It's not somebody trying to do this remotely. And at that point, the device opens and you can do anything with it. Does it answer your question?
Thank you.
Sorry.
So does the threat model include an attacker who opens the case and rewrites the AP flash and would it be possible to extend the firmware to use that MUX to validate the flash prior to releasing reset? And then as a follow-on, do you expect that bootguard and other hardware support will be enabled on these devices to further protect the flash?
Well, it's as far as the owner opening this up and replacing, I'm out of time, sorry. Opening this up and replacing firmware, there is no protection from this. Again, this is a Chrome OS concept. This is not a H1, something which H1 brings into the system. So, yes, if the user can replace the flash chip, they can do anything they want. But in this case, this will fail. Because, so if this AP flash was modified by the user, then these hashes will be wrong, and the H1 will highlight that. The bootguard, again, it's a completely orthogonal thing. It's something which H1 doesn't care about. This is the AP thing, and you know, if we decide, there are other people who can answer that question, like Duncan there, for instance.
Speaking of which, we have so many questions, but you know, time is few. We're going to have lunch now. It's a 90 minutes break, so you will also have enough time to keep on chatting about everything here. I guess you will be around.
Yes, I'm glad to answer any more questions. And by the way, Martin is going to give a talk about CCD specifically, right?
I've got to still organize it.
Okay.
Okay, perfect. So thanks again very much.